So what's the speed of a car? So I drew a diagram. I was like, so this radius is 50 meters. The car is here with a mass of 700, and constant speed in the central force provided by the friction is 11200. So that's like, it's insinuated, that's your FC. So FC equals mv squared on r, and you can just solve for v, r times FC divided by m. So 50 times 11200 divided by 700, and v is 2. Oh, sorry, this is like what you get in your CAS, but significant figures I'll always do around 3, because yeah. So what's the acceleration? So acceleration is just v squared on r, and we know v now. I chose to use like the full version of v, this one, not the decimal, but I'll just write the decimal point for simplicity. But yeah, I don't think it matters because it depends how many significant points you put it to, but you get, you get 16 if you put it with exact figures, but if you round it, you should get 16 anyway. So stock question 3. So there's this situation, and the block is released from rest. So it's gonna go this way, and this is gonna go this way. So what's the acceleration of the block? So we use F net equals ma. Since it's going down, this is like, you do this system minus this one. So weight force is 0.1 g equals 0.40 kg, because there's no friction, so there's no actual like force bringing it otherwise. So the only force is the weight force here. Sorry, equals 0.5 times a. We can isolate it to we can't isolate it, so we have to use the masses of the whole thing. So, and for this test we use g is 10 because it tells you at the start. So you get a whole number of 2. So what's the kinetic energy of the block m1? So ek is half mv squared, but we don't know v, so we have to use our constant acceleration formulas to find it. And sorry. The one thing we don't have is t. So the equation that doesn't have t is v squared plus 2as. So v is just this, and I just put this straight into here. So I said v squared equals 2as, and I put it straight into here. So ek equals m on 2as, which is just mas. So if you just put m is, so this is for block m1, so m is 0.4 and a is this one, and you get 0.8. So figure 2b is bicycle and a rider, and question 5 is draw 2 arrows to show the forces acting on bicycle and the rider. So the only forces right now would be the F weight and the reaction force on the surface. And you don't draw FC because that's the resultant force. So what should be the value of the angle on the bank of the track? So the bicycle travels around the corner when there's sideways frictional force. So the equation we know is Rg tan theta, and R is 100, G is 10, and tan theta is the one we're trying to find. And we know V is 10. So if you just rearrange this and do tan inverse, So tan inverse 100 on 100 times 10, theta is 5.71. So question 7, what's the speed of a car at point B? So like, since this is like a roller coaster question, you can kind of tell it's going to be, you equate the energy, total energy is conserved. So let E at A equal E at B. Those would be the easier points to use because we don't really know much about C, so we use A and B. So at A, the only energy is gravitational, and at B, it's kinetic because it's at the floor, so the gravitational is 0, and there's no spring force, so it's just those two. So mgh equals half mv squared. The m's will cancel, so it's asking for speed, so v is square root 2gh, and if you sub in your values, v is just 20. Question 8. So from point B, they travel up to point C, and the riders in the car have no weight. So point C is here, so the cart would be upside down. So Rebecca says they're not actually weightless. So I said Rebecca is correct. It's correct since they're still affected. I'll just write this in shorthand form. Still affected by Fg by Earth. So they're not weightless because they still have a weight force because they're in the gravitational field of the Earth. But feeling weightless is when Fn equals 0. This is true also as at point C, Fn equals 0. So like something along those lines, but yeah. So Rebecca is technically correct because they're not actually weightless, but they do feel like they're weightless, so that part is also true. So what's the speed of the car at point C to feel as if they have no weight? So at C, like the loop is here, so F weight is down, and Fn is also down, and so is Fc. So Fnet equals Ma, Fc equals Fw plus Fn. So Fn must be 0 if they feel like they have no weight. So mv squared on r equals mg, and v equals square root mg. Oh no, we can cancel the m, so it's just rg. So 10 times 10 is just 10. Next question. So there's a helicopter and it's dropping a rescue package. So it's traveling with this velocity and it's 200 meters above ground. So what horizontal distance must the hikers, from the hikers must the package be released? So there's two parts to this question. You have to figure out the time it takes for the package to drop, and then you have to consider that because that will be that will determine how far back they should be. So the time taken to drop, so vertically, use our constant acceleration formulas. So it's only moving horizontally, so because the height is constant. So vertically, the initial velocity and the final velocity, they will be 0. And A is 10 because it's just gravity that will be acting on, oh, sorry, I should write that. So this is vertically for the package. I'm going to get confused. So it's vertically for the package. So U is 0, but V might not be 0 because at the bottom it will have some velocity because it fell with this acceleration. And S is 200 meters, and we want to know T. So the equation that doesn't have T, V, we don't know V. is ut plus half at squared, and u is 0, so t is just square root 2s divided by a, and if you sub in these values, t I got was 6.32456 seconds. So now that you have the time it takes to go down, you can figure out the time, how far back they should be. So it's s equals ut plus half at squared horizontally this time. But there's no acceleration horizontally, so it's just pretty much distance equals speed times time. So distance equals u, we know is 10. They gave it to us, and time we just figured out here. So s is approximately 63.25 meters, but I'll just write 63. So what is the speed at which the package hits the ground? So we know the horizontal speed is always 10, but when the package hits the ground, it'll look like this. So there's a vertical velocity. So we can figure that out using the constant acceleration formulas of the package again. So like here, but we're trying to find v this time. So a is -10. This is 200. You can use your t value, but I'm going to choose not to in case I made a mistake here. So it'd be safer to just use a different equation that doesn't require t. So that's v squared equals u squared plus 2as. And if you sub these two, v is 64.03. So it's 63.2455. So this speed is 63.2455 down. And then to find the speed, you have to mod the vertical and the horizontal components. So I got 64.03, so I just wrote 64. So it's a game of tennis, and the ball is, so it's being thrown upwards here, and then at here the velocity is 0. Oh, sorry, it's actually being thrown like vertically up, so v equals 0, and then a racket comes sorry, it's an ugly racket, and hits it here, and so m is 0.057 kilograms, and we know that I is 1.7. So, and they also give us t is 0.008, and it's asking for average force. So easily the formula we know is impulse is force average times time. So F average is just impulse divided by time, which is 212.5. So I'll just round it to 213. So we have a spring question. So there's an ideal spring with 2 kilogram mass attached, and it's held is held so that the spring is not extended, and then it's gently lowered. So that means at this point it's in equilibrium, and it's at rest. So that's pretty much it. And then to find k, we know we just have to equate the weight force to the spring. So mg equals kx. So k is just mg on x. So m is 2, g is 10, and x is from here 0.4. So we just get k is 50. Next question, what's the magnitude of the total energy of the spring mass system between figure A and figure B? So in figure A, the total energy, so there's 3 things we can have. We can have we can have gravitational energy, kinetic energy, or spring potential. At A, there's no kinetic, and at B, it's at rest, so there's still no kinetic. But since we don't have a H0 line, like height 0 line defined for us, we can take this place where the figure B is as H0. So if we do that, then figure B also doesn't have gravitational energy. So we can equate the addition of these two things to this one. Oh, sorry. Half kx squared E. Trying to figure out what I did here. ES is mgh. Oh, right, sorry. There's no spring potential either because it's not extended yet. That's why. So I was checking why my working out didn't have ES. So yeah, so at A, we just have gravitational potential. So that's mgh. It's 2 times 10 times 0.4, which is 8 joules. At B, we just have spring potential, so that's half kx squared, so it's half 50 from the previous question, 0.4 squared, so that's 4 joules. So the difference in the total energy is 4 joules. And yeah, I think I was supposed to do my working out. Yeah, but anyways. So next question is a graphs question. So which graph best explains how the total kinetic energy of the system varies before, during, and after the collision? So we have this this situation, and we have these things that we know. So there's a light spring, and when it's uncompressed, it has a length of this. It's initially moving to the right. Trolley M2 is stationary. Then they collide, and the spring compresses, and then they move apart. Both trolleys move off. The collision is elastic, so that's important. So that means EK is initial is EK final, and there's no frictional force. So this point is what we're going to use for question 15. So it's asking the total kinetic energy of the system before, during, and after. So we know before and after should be the same because it's elastic. So if we look at the graphs, it can't be C, and we're left with A, B, and D. But the thing to be like note, I guess, is that when they compress, the trolleys like slow down a bit, because at this point here, like where the spring was, when it's compressed, some of the EK is converted to ES, and then when the spring like doesn't extend anymore, then the ES is converted back into the EK. So we're looking for, so it can't be B because it changes, so it can't have been the same the whole time. So we look at the different things, and we know we're losing EK and then gaining it. So it's A, it's not D because we would be gaining EK before we lost it. And that would make sense because there's nowhere to gain it from. So the answer to 15 is A. Explanation would be what I just said, but like if I were to summarize, some EK, okay, we should write collision elastic. So EK initial is equal to EK final, and some EK converted to ES, then back to EK when spring compresses. So now it's asking for the total momentum for, during, and after, and we know that momentum is always conserved, so like there should be no changes, so it's B. For the explanation, I will just write momentum always conserved. So if the collision had been inelastic, what would be the magnitude of the total momentum? And the answer is still B because momentum not dependent I should write momentum conservation is not dependent on kinetic energy, so would be conserved even if inelastic. And yeah. Oh, and I think the answers also said you had to also add because there is 0 external forces on the system. So like, because momentum is only conserved in a closed system, so you have to mention that as well. So now we're on to gravitational forces and fields. So we have International Space Station. It's under construction, so it's being made in the orbit. It's incomplete and it has a mass less than what it would be when it's finished. And it has an orbit from the center of the Earth, so that's good because we don't have to add the radius of the Earth then. So what is the weight of the International Space Station in its orbit? So weight force is mg, but we don't know what g is because it's not like on the Earth's surface, so it's not, g is not equal to 10 anymore. So we know the mass. I'll write the equation without the numbers first. And the equation for g is this, so we can sub in numbers. And m, the big M, is the mass of the Earth, so that is 5.98 times 10 to the 24. And the radius is how far the space station is, and we don't need to add anything to that because it's already from the radius of the center of the Earth. And if you do that, you get 2.9669 times 10 to the 6, and that's your answer. So what is the period of the orbit? So we can get that equation if we equate these two things. We know how to do that. So, but the final equation we would get is this one. And R is 6.72 times 10 to the 6. M is again the mass of the Earth, because once you equate them, the little m, which is the International Space Station mass, that will cancel. 24, and you get T is 5.48 times 10 to the negative 3, which seems really small. So let me just double check that that's correct. I'll just move on to the next question. Do that. So when ISS is completed in 2011, its mass will have increased to 3.7 times 10 to the 5. But as we determined here, that will have no effect on the period because it's not dependent on that. So it will be the same because, again, as I said, I'll just write it so we know what happens. So FC equals F weight. Oh, no, that's why. I mean FG, sorry. FG, so MV squared on R equals GMM squared. You can see the M's already canceled, but if we're trying to get the formula for T, we can do 4 pi squared R squared T squared. So T squared equals this one. T squared is equal to this, but yeah, and that's how you get the T formula. This is actually about 3. I was reading my handwriting wrong. And yeah, so this is the same because nothing happens to it. And that's the